Hi there. No live lesson today. Instead, this recording. Thin film thickness. We're going to do some calculations, and I'm going to go over some theory that I did last week. But this bit of theory is just the same as last week, but it's a little bit more rigorous. Might be better for some of you to understand what's going on. Okay, so we've got our thin film, which we've got air, and I've got oil, and I've got some oil sitting on a layer of water, and the refractive indices are 1, 1.45 and 1.33. So we've got our beam of light, incident beam of light coming in here. First ray goes off that way, second ray goes off like that. Okay, and we're looking to see if there's interference when these two rays come back. Okay, so if we've got the thickness of our film is D, then we know that the optical path difference is there and back. That's 2D multiplied by the refractive index of the film of oil. So we've got our optical path difference is 2ND, and then we need to have a look and see if there's a phase change on reflection. So we're going to look at this first one, ray 1, which reflects from the air-oil interface. So we're looking at low to high I. So there is a phase difference of half a wavelength for ray 1. Ray 2, that's high to low no. So there's our total optical path difference. Now for constructive interference, that has to equal a whole number of wavelengths. So I'm going to do 2ND plus lambda over 2 equals m lambda, like that. And then we can rearrange that. 2ND equals m lambda minus lambda over 2. This is what I didn't really do last time, but I think mathematically this is more rigorous, and you can see what's going on. 2ND, we take out a factor of lambda, and we get m minus a half, like that. And then we can rearrange this because I want to work out the thin film, the actual thickness of the film. So I want to make D the subject of the formula. This is what we didn't do last week. So I'll go up there, rearrange the formula, and I've got D is equal to m minus a half lambda on top divided by 2n on the bottom. And n, remember, is the refractive index of the film of the oil sandwiched in the middle. So this is our constructive interference thin film thickness formula. Now what we need to do is look at what are the values of m that we can have here. Now we ought to be able to have m is 0, 1, 2, 3, any integer we like. But if we put m is equal to 0 in here, we have 0 take away half, we end up with a negative number on the top. So that's not a solution, is to have a negative film thickness. So 0 is not a solution for this particular film. If we then go on to m equals 1, we have 1 minus a half, which will give you a half lambda on the top divided by 2n. Now that's the first solution. That's the first solution. Now if m is 1, that gives us the thinnest film we can possibly have. And this is a common problem for advanced hire. What is the thinnest film of oil you could possibly get away with for constructive interference? If you have m equals 2, then that just makes this larger, and so D becomes larger. So m equals 1 is the thinnest film solution. Okay. And we can't have naught, and anything bigger than 1, 2, 3 or whatever just makes this whole thing bigger, and then we get thicker values. That doesn't mean to say that you can't have a thicker thickness of oil, but it's a common question where they're going to ask you what's the thinnest film, and you've got to work out that if you rearrange excuse me rearrange the formula that we looked at last week, putting m equals 1 will give you the thinnest film. Okay. Now for destructive interference, remember the formula just says on the sheet, it says m lambda or m plus a half lambda. Doesn't tell you which one's which, doesn't tell you where to use it. That's where you've got to analyze this situation. So for destructive interference, we're going to put our optical path difference 2nd plus lambda over 2. We're going to put that equal to m plus a half lambda, and then we can rearrange that. So 2nd equals m plus a half lambda minus lambda over 2. And it might be helpful to expand that, or you might be able to see what's going on here. Here I've got plus lambda over 2, and here I've got minus lambda over 2. You can expand that if you want to, in which case you would get m lambda plus lambda over 2 minus lambda over 2. The 2 lambda over 2's cancel out, and for destructive interference you get 2nd is equal to m lambda. Now what's the thinnest film you can have? Well, once again, we can start off with m equals 0, but then 2nd is equal to 0, and that's not the thinnest film because it's no film at all. So the thinnest film, once again, will be when m is equal to 1. So we could have a look at some calculations now to actually work out what is our film thickness. In this case, this is m lambda over 2n. So for constructive interference, our film thickness is whatever it was I said before. I rubbed it out now, I can't even remember. Doesn't matter, we'll come back to that in a minute. So you can take the two formulae and put m equals 1. Let me go back and have a look. I'll just see if I can find it. I've got it written down here. Can't remember all this off the top of my head. Constructive interference, d is equal to m minus a half lambda over 2n. And for destructive interference, d is equal to m lambda over 2n. And n, once again, is the refractive index of the oil floating on the top of the water. Okay, so this is just me restating what I said before. Okay, so for problems, what we want to do is all we really need to know is what's the refractive index of the film and what's the wavelength of the light. So you can pick a wavelength of light. Let's have a wavelength of light of, say, green light. And we will come on to later on what happens if you do this with white light in sunlight, but just for now we'll just take a particular wavelength of light, and we'll take that as 525 nanometers. which, as you probably know, is 5.25 times 10 to the negative 7 nano is 10 to the negative 9. And then you've got an extra 2 decimal places there to take off the 9 to give you 7. So that's meters. So and oil, which we had previously, which was N is 1.45. You'll either be given these in the question or you'll have to look them up in the data table that you get. So just be aware you may not be given these. Be prepared to look them up. And oil is sometimes labeled as glycerol, but it would then say glycerol in the question. It wouldn't say oil in the question and then glycerol in the data table, and you're expected to know one is the same as the other. So we're going to put M equal to 1. And we can then work this out, and I'll let you do that. You can work out what is the minimum film thickness for constructive interference and also for destructive interference using these two formulae. You can make that simpler if you want to, but you can see how that formula reduces from that one. So I'm just keeping the 2n on the bottom. So you can work through, take a pause now, you can work through and you can find out what the thinnest film is for constructive and destructive interference with that data. And I think for the destructive interference, the answer works out to be 1.81 times 10 to the negative 7 meters, which is pretty thin. Okay. Now, in real life, you're not going to get just green light. You're going to get a range of lights. You're going to get red, orange, yellow, green, blue, indigo, violet, and the oil film is going to have different thicknesses. So what you will get is a range of constructive interferences and a range of destructive interferences for different color lights, because lambda is going to be different, and also for different colored thicknesses. So what you'll tend to get is a sort of multicolor, two-dimensional rainbow effect. And I'm pretty certain that most of you will have seen this sort of thing where you've seen petrol or oil on a road that's wet and the sun's shining on it, and you'll get this multicolor rainbow, lots and lots of rainbow patterns. I don't mean rainbow like that sort of rainbow. I mean sort of swirly patterns which change direction and change colors. Not a rainbow that like you get in the sky. So be prepared to talk about why with white light you just don't get one particular effect. You're going to get a multiple effect with lots of different colors, because white light's made up of lots of different colors, and also the oil thickness will vary, and it's probably not going to be as thin as that all the way. It will get a little bit thicker, and you'll have different values of M, but you can't work out what all the different values of M are for every single bit of rainbow effect you get. Okay, right, I want to move on now to something slightly different. It's still about thin films, but it's thin films used in a practical application. And everybody's got one of these thin films probably sitting on the desk or in their pocket, and it's lenses in cameras that are coated with a thin film of chemical, which will cut down destructive, constructive interference and will stop you getting funny effects on your photos. So I'm going to move on to that. Okay, so the process of adding a thin film to a glass lens, let's just have a a look at a glass lens. There's a lens, and what you would do is coat it with a very, very thin film of chemical, see-through chemical, usually something like magnesium fluoride. And magnesium fluoride is actually given in your data table with its refractive index. So the way they do this is that you take a glass lens and the lens goes in an oven, and the magnesium fluoride is introduced as a gas, and the lenses go around on some sort of carousel system, so the lens gets coated nice and evenly on both sides. It gets this coating of magnesium fluoride on it, and this magnesium fluoride builds up, and then you take the lens out of the oven and you've got a coated lens. This process of coating a lens with a chemical to prevent unwanted interference effect is called blooming. And the technique that you end up with the lens, and the lens coating is called an anti-reflection coating. If you go to the opticians, if you wear glasses, the cheapest lens you can get for your glasses is just a plain, normally plastic these days. Not very many lenses in glasses are made of glass anymore. They're made of plastic, and they're coated. And this is especially useful for driving at night, because you can get lots of reflections. It's bad enough driving at night when you've got car headlights shining at you. And if you wear glasses, you get lots of either glare, something called glare, or something called flare. And either way, you get multiple images of headlights, and it's very, very distracting. You can also get the same sort of thing for glasses. Sunglasses, if you're down on the beach or you do a lot of water sports, they're very useful for that, and also for ski goggles, because there's a lot of glare that you get off the sun, and you don't want off the snow with the sun, and you don't want to get all this glare. So the better glasses, goggles, sunglasses all have this anti-reflection coating applied. So we're going to go back to our diagram that we're very familiar with now, and we're going to just have the air here. We're going to have our anti-reflective coating, anti-reflective AR, and we're going to have glass. It's probably not glass, as I've said. Probably is glass for camera lenses in your smartphone, but it's probably more likely to be plastic for ski goggles and what have you, because they bend a little bit. The lens is slightly flexible. And we've got some different refractive indices to consider. Again, we've got n equals 1. Normally, I think if you look up this magnesium fluoride in the data table, I think it's something like 1.38, and you've got your glass at the bottom, which is, or perspex or whatever, plastic, is about 1.5. Having these coatings put on, it makes the lenses more expensive. So if you go to somewhere like Specsavers and they say, right, here's your basic price, what would you like? Would you like your lenses to be tinted? Would you like them to have the anti-reflective coating? And the price goes up and up and up, and before you know it, the glasses, which have a headline price of about £55 or something, suddenly become 110. They've doubled in price. So once again, we've got our beam of light coming in here, one going off like that, the other one coming through like that. Okay, so we know that the optical path difference once again is 2nd, and then we've got to look at any phase change. So we're going to do look at this low to high I, so we get a lambda over 2 there. Low to high I, so we get another lambda over 2 phase change there, and that means they cancel out, because a whole wavelength difference is not a difference at all, really, because the waves are still in step. They're just one wavelength different from each other. So there's our optical path difference is 2nd, and what we want to do with these lenses is we want to stop this interference. So the way to stop it is to make sure that you get a lens thickness that gives you destructive interference, and then that means that cuts down on light that is being reflected. You don't want constructive interference, because then the light that you see in your eye would be even worse. So you want a lens coating that's set up for destructive interference, and our destructive interference formula, as you all know by now, is m plus a half lambda, and we can rewrite that to get our lens thickness, m plus a half lambda on top and 2n on the bottom. Right, so what would be the thinnest coating we could have? Because you don't want to spend a lot of money putting a big thick coating on. You want the thinnest coating you can get away with. So once again, we need to look at our possible values of m that we can have. And if we put m is equal to 0, then that's a positive part there, and that's all works out very nicely. So we'll put m equals 0. And then our formula is d is lambda over 2 divided by 2n. Now, previously, I didn't bother rearranging that, but we can rearrange that quite nicely to give d is lambda over 4n. And I think this formula, I'd need to go back and look, I haven't got it in front of me. I think this formula is actually given on the formula sheet for the thinnest coating to get a non-reflective or anti-reflective coating. And n is the refractive index of the coating, in which case that would be 1.38. So what's the thinnest coating you could get away with in terms of calculation? D equals lambda over 4n is our formula. Let's pick a wavelength of light. Let's go for some sort of green light again, where lambda is 520 nanometers. That is 5.20 times 10 to the negative 7. And so we'll get D is 5.2 times 10 to the negative 7, all divided by 4 times 1.38. And that is equal to 9.42 times 10 to the negative 8 meters. Now, that's extremely thin coating. And there's some special way of measuring how thick that is. I think it's to do with this magnesium fluoride. It goes into your oven as a gas, but it obviously condenses onto the lens as some sort of crystal. And it's possible to measure the crystal size for the length of time that the lens is in the oven. So you end up with this optimum thickness. Now, that's just for green light. Obviously, if you're out skiing or you're driving, you see headlights. Headlights are white, sunlight's white, the glare off snow is white. If you're down on the beach, the light tends to be, it's double glare. You get glare from the sun, you get glare from the sand, and you want to cut out that glare. So that implies you've got a whole range of different wavelengths of light, and you can't have a variable thickness lens. You can't have a lens that's got a thickness of film on for red and orange and yellow. So you can only have one thickness. So what thickness of film do you put on? Well, let's have a look at our spectrum of light, and you'll see that green is right in the middle. So of the optical spectrum, the visible light spectrum. So if we put this thickness of film on, that's going to cut out all green, but it also cuts out a little bit of the yellow and a little bit of the blue and a tiny bit of the orange and a tiny bit of the indigo, but it hardly cuts out much of the red or much of the violet, because it's not what's called an optimized thickness for these other colors. So if you see a coated lens, and if you just if you took a lens out of a camera, for instance, I don't mean take a lens out of your smartphone camera. If you saw a lens from a big professional camera where the lens is probably, you know, sort of that big, and you hold it to the light and you tilt it slightly, the color of the lens will be a mixture of red and violet, because you won't see any green light. Green light is destructively cut out, and a little bit of yellow and blue, and you'll tend to see this sort of reddy orange and indigo violet color. So we'll just stick, to make it a simpler definition, we'll say, right, we cut out most of the light in the middle. We're left with a bit of light here, which is red and violet, and red and violet added together give a sort of purplish color. Can't spell purple. Give a purple color. And so the lens, you can tell a good quality lens by holding it up to the sunlight, and if it appears to be a purple color, you know it's got some good coating on it. So that's primarily the way in which you will cut down on light and reflected light with lenses. Now, there is a more, this is the way that they want you to do this in Advanced Higher. They want you to think about what's the best color to try and cut out, and it's green because it's in the middle, but you get these other colors. So this is something you need to learn for Advanced Higher. Practically these days, they don't do this with lenses, high quality lenses. They do actually have multiple coatings on, which cut out a lot more of the extra colors. And indeed, the coating colors that are cut out with modern glasses from Specsavers, if you hold up a Specsavers pair of glasses that's been coated, you actually won't see them being a purpley color. They appear to be a greenish yellow color, because you've cut out these and you've cut out these colors rather than the color in the middle. But for Advanced Higher, if you get asked a question in the exam, why do lenses that have had this blooming process, why do they appear purple? You can now discuss that you're going to coat it with one coating, which is optimized to give you destructive interference, so you don't see the green, but you see the colors at either end. And you can talk about that. You don't need to talk about what really happens in real life now. And that's that. Okay, right. That's anti-reflective coatings out the way. And that's that sort of section finished now, where we're looking at these different layers of air and some material and glass or whatever, and they're in nice layers that are the same thickness all the way along. We're going to have a look now at something different, which is called wedge fringes. And a wedge fringe, this was first noted by Newton. I've talked about this before. This was first noted by Newton when he was looking at making really perfect lenses. And he found that if you took a glass lens like that and you put it onto a piece of glass like so, you've got a gap here, you've got an air gap here, and if you're looking down on this from above, you'd have your round lens sitting on a square plate of glass. So that's a square plate of glass from the side, and that's a lens from the side. And when you look down through the lens, you'll see constructive and destructive interference set up because of this gap here between the two bits of glass. And you'll get this sort of bullseye picture that I mentioned before. And if the bullseye picture is nice and regular with what's called concentric circles, which means circles like on a target with a bullseye in the middle, and the lines are nice and regular, not like mine, which are a bit wobbly. If they're nice and concentric, you know you've got a nice perfect lens that you've shaped. Newton didn't have a way of making shaped lenses like they do now. You can get shaped lenses made very, very quickly with plastic. But Newton had to take a block of glass and then he had to spend hours and hours and hours rubbing down with really very, very fine grit, a bit like sandpaper in effect, where you would rub down a block of glass like this and you'd start shaving it off. So you'd end up with a lens shape. And then the finer grit that you used actually doesn't scratch the lens at all. It just polishes it up. And it's the same as using car wax, not car wax, but you get special stuff from garages called T-cut. If you've got a car that's been in the sun a lot, the color tends to fade, and so you can use this T-cut material, which is a liquid with a really very, very, very fine sort of grit in it, and you rub that on the car, and all you're doing is you're rubbing off the oxidation layer of paint on the top to bring out the color back again, and then you put the wax back on the top. You can get that done professionally. I don't think many people do it these days because I think the coatings on cars to prevent that oxidation and the color changing tends to be much better. So you get these rings. So that's called Newton's rings, and it's really this bit, this sort of wedge shape that I want to look at here. And why do you get that? Now, mathematically, that's quite difficult to analyze because you've got a changing curve here and you've got a flat bit there. And what I want to do is actually, instead of looking at this changing curve, we're going to look at as if you've got a piece of glass here and you've got your other piece of glass underneath. And instead of having a curved surface here, we're going to have a flat surface there. And we need to prop this up somehow at this end. So I'm going to take something. You could take any thin object. What you want is a really thin piece of glass here on a block. And typically for SQA advanced hire purposes, they'll say, right, we've got this piece of glass here propped up on another piece of glass, and we're going to prop it up with a human hair, or we'll prop it up with a very, very thin piece of like tin foil or something, or a thin piece of paper, just to make this into a wedge shape. So this is called an air wedge, and this is air in the middle, and obviously it's two bits of glass there. And what you'll get when you look down on top of this is, because this is a straight piece of glass, looking down on top, it would look like this. You've got a base of glass like that, and you probably have just something like a glass microscope slide propped up with perhaps a human hair to prop it up to make a very, very thin wedge shape there. And because it's such a thin wedge, this is sometimes called a thin wedge or a thin air wedge. And so you'll see this described as wedge fringes or air wedge fringes or thin air wedge fringes. And what will you see? What you'll actually see is, instead of a circular pattern like that, you'll see lines. You'll see an interference pattern that looks a bit like that. Okay, that's not a very good diagram, and I'll come back to that later because the spacing isn't quite right on that diagram, but that's what you will see. This has formed the basis of previous advanced hire projects where you can set this up with monochromatic light and you can measure the spacing here. And this is what we're going to do in theory now. We're going to have a look at measuring the spacing here, and from measuring the spacing of the fringes, you can actually work out what the thickness of this piece of material is, human hair or a bit of tin foil or whatever. You work out the thickness of it by measuring the interference fringes. So let's have a look at this again, just for a change. I'm going to draw it the other way around. I've got my piece of glass on the top and a piece of glass on the bottom. I'll finish that one there. This one can go on somewhere, it doesn't really matter. And we'll prop it up with a human hair like that. So what's going to happen, this will be very, very familiar. We're going to get light coming in here, and the most obvious interference pattern is where you get the light reflecting from there, and the other beam of light, which is going to set up our interference, is going to reflect from there. So the two reflections are from the bottom of the top slide and the top of the bottom slide. Okay, bottom of the top, top of the bottom. Just to reverse it, that's where you get the interference seen most remarkably. Now, of course, there will be other reflections. There'll be a reflection from this top surface. There could be a reflection from here, but these don't really set up a strong interference pattern. So we're only going to look at the reflection ray 1 from the top of the bottom slide, and ray 2 is going to be from, I've just said that completely wrong, the bottom of the top slide and the top of the bottom slide. So ray 1 and ray 2, they're reflecting like that. And of course, once again, we're splitting them up like this. In reality, the ray of light would just come down and go like that, and you wouldn't see where it reflects from. So we're just taking it like that so you can actually visually see what's going on. And what you'll get to see, looking from, that's the side view, what you'll get to see looking down from above is you will see an interference pattern. But because this wedge here of air is obviously thin, it's very thin here, and it's thicker there, the interference pattern is not regular. The spacing changes. And so here, I'm going to draw this. This is a dark fringe here, and you get a dark fringe where the two bits of glass touch. And then that will start to fade out, and I can't do the fading out bit, but then it will fade back, fade out. This is sort of back to front. It's dark, and then it starts to get progressively lighter. Then you've got a nice bright fringe, and then it fades out to dark again. So these are dark bits. These are dark bits here, and the spacing goes something like this, I think. Okay, spacing goes something like that. So these are dark fringes like that. Now, in reality, you can't see this just looking with your eye. What you would have to do is you have to set up a microscope above here to see these fringes, because this wedge is so thin, the fringes are so small. It's not like the lens with Newton. So a microscope is used here, and the microscope would be set up so you can see that. Set up the microscope here, and your eye is looking into the microscope. There's one lens of the microscope, and so you're going to use the microscope, and you would use the microscope which travels along, so you can observe these fringes. And because the microscope can be set up, not only does it go up and down to focus, it can also move from side to side. And so the piece of equipment that you use to observe these fringes is called a traveling microscope. Why is it called a traveling microscope? Because you can move it from side to side. And when you move it from side to side, we've got one of these in the lab, and it's usually something I set up with a monochromatic yellow light source and the traveling microscope, and you can actually look down the microscope and you can see this. But the traveling microscope is actually connected up to a very, very sophisticated measuring system with an incredibly accurate set of, basically it's like a ruler, but a ruler with very, very fine divisions on it. So the traveling microscope has what's called a vernier scale. It's a vernier ruler scale. So you can set up the microscope and you can set up the crosshairs in the microscope. It's not just an ordinary microscope. When you look down it, it's actually got some crosshairs, and you set up the crosshairs onto one of your dark fringes, and then there's a dial at the side, and you turn the dial and the microscope physically moves. It travels along, and it travels along till you set it up on the next fringe, and then you can travel and set it along on the next fringe. And what you do is you take a measurement right at the start on your ruler. And I'll just give some very, very basic numbers here, which are nothing like the numbers you see. But so I set that up and it says 0.2 there. And then you make the microscope travel along 1, 2, 3, 4. And it might get to here and you take another measurement, which might be 1.0 when you get to the next one there. And you take 0.2 away from 1 and you get 0.8. And then you can say, oh yeah, I've got 4 gaps there. So what's called the fringe separation is 0.8 over 4, which is equal to 0.2. But the measurements are much, much smaller than that. So you can physically measure the distance between the fringes. Okay. So this is some of the language that you might see in a question with the traveling microscope, the vernier scale. Because I can't actually show you this, I've got to explain it. I'll have a look for some sort of video. I haven't looked yet to see if there's a vernier scale traveling microscope example of this setup. I know I've definitely got a computer simulation, but I'm working on trying to get the computer simulations, which only work on PCs. I'm working with a colleague down on the Murray Coast in a different school to get these computer simulations to work on Chromebooks. We've had some success so far. Okay, I'm just going to stop here to gather my breath. So I'm going to stop the recording. I've given you an idea of what's going on, and then I'll come back in the next recording with the maths of the thin air wedge fringe, because we're going to use this idea of being able to set up our traveling microscope to measure the distance between these fringes, and using some trigonometry, we're going to, as I mentioned earlier, we're going to use that to work out what is the thickness of the object that's sitting in here. But I'll stop that for now, gather my breath, and come back and start again shortly.